All right, thank you very much. Let me start by thanking the organizers for their hard and very successful work of putting together this conference and also the preceding workshop. We've been having a great time here. Thanks a lot for that. I'd like to talk today about these three recent papers done in collaboration with my student Sven Krause from Heidelberg, with Christoph Meyerhofer, who's a postdoc in Heidelberg and who's also participating in this conference, and with my student Max Kersten, who's also here and who covered part of what I will be discussing at the end of this talk on Tuesday. So to begin with, I would like to stress that investigating local and global issues in F-theory phenomenology is really not in contradiction, but this is something that should be considered as going hand in hand. We saw in a number of nice talks yesterday and today that many important phenomenological aspects in F-theory model building are indeed governed purely by the local data of our compactification. This is fantastic because we can learn a lot without specifying the UV boundary conditions, if you like, in detail. On the other hand, however, it is also well known, it has been known in string phenomenology for a long time, that there are other important ingredients in model building which do depend on global aspects, in this case on global aspects of our geometry. These are known to include, for example, the physics of abelian gauge symmetries, which are important because they have an imprint in terms of selection rules in our gauge theory. It includes in this case, physics or mathematics of gauge fluxes, which of course are crucial to get chirality and crucial ingredients in our model. And it also, global aspects are also important to study instanton effects, as we heard earlier this week and today in a number of talks. Instanton effects are not only important for moduli stabilization, for SUSY breaking, all of which are manifestly global questions, but they are also important in the context of generation of couplings, selection rules, etc., something that looks like it's really only dependent on the data of our gut manifold. But in particular, Fernando's talk today, I think, was a prime example that showed that even though we have an effect that looks like it's far away, we have an instanton that is far away from our gut brain, nonetheless, it made a difference how this is really completed, if the instanton intersects one of the metabranes or not. And as he discussed, there are two different effects. So we really need for certain effects full information of our model. Indeed, this is whenever physics or something depends on stuff that is not localized on our gut brain. This is basically pertinent to all these 3 points. So to address these phenomenological issues in this talk, I would like to go back a step and actually focus more on the geometric aspect of the compactification. I will start by discussing the singularities of the fourfolds and their resolution for SU5 models and for SU5 times U1 models. This will then put us in a position to construct gauge fluxes, which we definitely need for model building. I will then pause a second and compare this with Type IIB limit, and I will motivate and tell you why this might be interesting. And finally, I will discuss aspects of M5-instantons and in particular selection rules for the superpotential. So the framework we'll be working in is the usual one, namely F-theory compactified on an elliptic fibered Calabi-Yau fourfold over 3 complex dimensional base. We will describe this elliptic fibration as our beloved Weierstrass model with projective coordinates x, y, and z in the fiber. So my z is what was, yes, so I'll call this z and not w as opposed to Sakura, just so you don't get confused. If we restrict 2 models with an SU5 singularity over a particular divisor, w equals to 0 in the base, the gut divisor, then it is useful to actually study the so-called global Tate equation. The details are not so important. What is important is that the complex structure moduli are now encoded in these global sections AI, which depend on the base coordinates, which are sections of the intercanonical bundle on the base. In particular, in order to engineer an SU5 singularity along a gut brain, it is known by the Tate algorithm that one has to constrain these AI in a specific way. The discriminant then factors into 2 pieces, the gut piece and the I1 locus, which contains all the other branes of our model. However, we want to go beyond SU5. We just heard that extra U1 symmetries are important, have important imprints in phenomenology. In order to do that, we actually have to do a major surgery in our model. This is something that cannot be done globally in any way. The simplest example would be SU5 times U1X model, more or less B minus L, so I will not be discussing the Peccei-Quinn type. And it was shown in this paper that in order to get this, we basically have to disallow this term A6 completely in our manifold and get a so-called U1 restricted Tate model, and I will discuss how the U1 comes about. And this is also, I think, interesting for more formal or general reasons. Okay, so far about part one, the geometry. In addition, we need fluxes. We need gauge fluxes described by MF theory duality, as Thomas reviewed today, in terms of a G4 flux, an element in H22 of our Calabi-Yau fourfold, subject to the extra constraint that it must have one leg along the fiber, so we can't take any four forms, we need to take four forms which are orthogonal to two base devices and also to the fiber. So it is here that essential information about the geometry, global information about the geometry really comes in, because we need to know this fourth cohomology group, which is a very complicated object. It is known in general terms that for a Calabi-Yau fourfold, H22 splits into two pieces, the so-called primary vertical subspace and the rest, the orthogonal complement of this. And correspondingly, there are two types of fluxes which also have rather different properties. H22 vert, the vertical piece, is contained or spanned by elements, by four forms which factor into wedges of two forms. Correspondingly, the resulting fluxes are called factorizable fluxes, and it is these factorizable fluxes that we really need the resolution procedure for in detail, because we need the two forms that we get by this resolution to write down those fluxes. And basically, there are two examples of such fluxes in the literature at this moment, and I guess this more or less exhausts the classification. On the one hand, whenever we have a U1 symmetry in our theory that is not, no, this is actually not true. Whenever we have a U1 symmetry in our theory, a massless U1 symmetry, then this will give rise to corresponding gauge flux, and this gauge flux will be in this space, and we will discuss this. In addition, there can be fluxes that are not associated with U1 symmetries and nonetheless are factorizable in this sense. I will discuss, or I will quickly review these. I was assuming that Sakura had done this. These are extra special fluxes called spectral cover fluxes. They were a little bit of a headache because we didn't know how to actually interpret them in brain language, but I will discuss this in a second. And finally, there is then all the rest, the non-factorizable fluxes. These fluxes, these horizontal fluxes, are considerably more complicated to get. They are also the more generic fluxes in the sense that there are far more of those in H22 than of those. They were pioneered in this paper, and we discussed them in the SU5 context in this paper. The good news, though, is that for model building applications, H22 vert is oftentimes enough for our purposes. We'll see this. So I motivated the necessity to resolve singularities because we need to construct fluxes. And indeed, with this motivation and also the motivation of making contact with an effective action, as beautifully described by Thomas today, with this motivation in mind, indeed the resolution of the SU5 singularities in our F-theory GATT fourfolds was tackled early on, as early as in 2009. And the first examples with completely resolved fourfolds were given in a toric context, in the context of elliptic fibrations of a specific torically embedded basis. Indeed, since then, a lot have happened in this field, and there is a large number of examples of this particular type constructed. And I should really point out once again that these models are completely resolved in codimension 1, in codimension 2, and in codimension 3. Irrespective of that, and thank God there was a lot of renewed interest in resolutions beginning in the past year, the motivation was to get an explicit handle on the singularities, in particular in codimension 2 and in codimension 3, which these singularities had been resolved, but this resolution was not, this particular structure of this higher codimension object wasn't made completely manifest in these works. And as of now, there are three, I guess, more or less independent, but definitely equivalent approaches to this problem. Sakura quickly discussed their approach of algebraic resolution by blow-ups and small resolutions. I will focus on our approach, which is an algebraic resolution by a sequence of blow-ups. And Grimm and Hayashi refined the toric resolution procedure and also got the same results. So the analytic resolution of singularities. Our approach is inspired, in fact, not by Isoli-Yau, but by the Tate algorithm, which had been around for a while. And as I said, it proceeds by a sequence of blow-ups, and it is valid for an arbitrary base. So this is not an approach that can be applied only to toric manifolds, but it's valid for an arbitrary base. This is important because we get arbitrary expressions for the fluxes and various integrals, which we can then compare with, say, type IIB and draw general conclusions. So since this wasn't covered in so much detail, maybe I should very quickly describe the general logic about this, but without going into too much detail. First of all, toy model SU2s. Let's suppose we just have an SU2 singularity. So in that case, our Tate model takes this particular form. We only have lower powers of W appearing in our Tate polynomials. And it is obvious that this hypersurface is indeed singular. It is singular at the point x equals y equals 0 in the fiber over W equals 0, which is in the base. So we have a singular point fibered over a divisor in the base because the polynomial and also its gradient vanish. So to do this, one blows up, one introduces one new coordinate together with the corresponding scaling relations in this manner. And this scaling relation makes sure that the singular point is removed, so to speak, and indeed replaced by a resolution divisor. This new coordinate E1 equal to 0 now gives the resolution divisor, which is a P1 fibered over the singular locus, and which changes the fiber structure over the formerly singular locus. And the result fourfold we then get simply by plugging this into our original equation. So this can all be done very explicitly. In order then to go on to SU5, we have to restrict our Tate polynomials even more. After one step, we are basically not done yet. There are singularities remaining. So one needs to perform a sequence of 4 blow-ups altogether, but the details change a little bit, but in fact it's the same thing again. We get 4 new coordinates corresponding to 4 new resolution divisors. So H11 increases by 4, and therefore also we get the possibility of extra fluxes. Now this was SU5, but we don't only need SU5, we need SU5 times U1 for the reasons I discussed. So to get this extra U1 factor, we have to switch off the term A6 completely. It now turns out that there is an extra singularity remaining. It's a singularity over a curve, the curve where A3 and A4 vanish. One can check this. This is a curve of SU2 singularity. So one extra blow up is required. One blows up in this fashion now, and again gets a new resolution divisor. This resolution divisor now is very different from the ones we had before because we were blowing up over a curve. It is a new section. In other words, a copy of the base, which is isomorphic to the base, except for the fiber over this singular curve where we have a P1 inserted. So the message is after resolution, we get 4 plus 1 new divisors, 4 from the SU5, 1 from the U1, and we will use these to construct fluxes. Very quickly, Sakura beautifully captured this, discussed this already. These resolution divisors, the ones that come from the SU5, have the property that they are IP1 fibered over the original surface. They intersect like the Dynkin diagram of our affine gauge group. In higher codimensions, some of these P1s actually split and form affine Dynkin diagrams of various other groups with a few surprises in higher codimension, which, however, are not so important. And indeed, one can now form various combinations of these P1s and identify them with the various weights of the different representations localized on those curves. Altogether, this gives us in codimension 2 a surface, namely a set of P1s fibered over this original curve where the splitting happens. And these surfaces are then the meta surfaces on which M2 branes are localized. Okay, and here again a cartoon from our paper. So here we have the SU5 with this SU5 fiber enhancements to SO10 and SU5 over various curves. But then in addition, we have this curve of SU2 singularity. This is non-local. It's not on top of the gut brane. It goes away. Here we have this extra SU2, and this symbolically represents this extra section, if you like. Okay, so why actually, I told you that we get this extra S divisor and after setting A6 equal to 0, but what does this have to do with U1s? I didn't tell you at all. So to see this, one again has to go into the M-theory picture and recall that U1s in the effective action arise from expanding the M-theory 3 form in terms of two forms which are not in the base and not entirely in the fiber. So all new elements of two forms that we get by this resolution procedure automatically give rise to new U1s. 4 of these are the Cartan U1s of our SU5. These are boring, but we now have one extra two form, which is the dual to our extra resolution divisor, and this is the one which corresponds to this extra U1x. In fact, one cannot take S itself. One has to take certain linear combinations involving also the fiber, the intercanonical class, and suitable combinations of these EI to normalize the U1 properly. This is just a detail. And at the end of the day, this extra resolution gives us an extra U1, and the various metastates that we have pick up U1 charges. These U1 charges can be computed. They are given by this two-form dual to this combination of resolution divisors over the P1 corresponding to the meta curve on which the M2s are wrapped. And let me point out in particular that apart from the SU5 meta, we now also have one singlet here. This singlet is localized away from the gut brain. It is manifestly non-local. It can play important roles, for example, as neutrino candidates in the context of SUSY breaking, etc. So these are extra singlets that are directly and reliably computed in this context. So we have the extra U1. What about now the flux? Finally, the flux. As soon as we have the U1, we almost trivially get the flux, namely just the flux associated with the U1, just like in type 2b. We simply take a wedge product of a 2 form on the base and this extra resolution 2 form. And this is just of the type, as I advocated, as a factorizable flux in H, 2 vertical. The importance of this flux, of course, is that, among other things, it induces chirality. Thomas described how to justify that the chirality of a given representation really is given by the 4-form flux integrated over this meta surface. Now, with this machinery, one can actually compute this explicitly. One can perform this computation. What one gets is that the chirality is just given by the flux in the base over the curve in the base times the charge. And this is exactly the same formula that we know very well also from type 2b. So we have reproduced this to a very simple general formula, and things are just like in type 2b. This is in particular important because it now gives a reliable computation of charged singlets away from the SU5 brain. And in fact, by comparing this approach to the previously developed semi-split spectral cover approach, we found that indeed the global geometry accommodates corrections which are not taken into account correctly in the split spectral cover. The reason is that the split spectral cover is insensitive to all the classes that happen away from the gut brain. So in the split spectral cover formula, one got manifestly wrong expressions which are corrected. And in this sense, one really needs the global details. So one can now play all the games with these fluxes that we love and enjoy from model building with brains. Quantization is a surprisingly complicated question that was virtuously and fantastically solved by Colin Savelli. We heard a nice talk on that. One can compute the D3 and M2 tadpole explicitly and as a general expression that depends on the gut brain and the intercanonical class on the B on the base. One can compute the D term, so the supersymmetry condition, thank you, with basically the same expression. And once one has this, one can easily construct globally defined examples, say 3-generation models in this context, over in concrete fourfolds, because the base, once again, was arbitrary. We can just take it, for example, from Christoph's list or from the list we had produced previously. And even more, one can now go ahead and classify the possible fluxes in the setup, not only for SU5, also for other SU-N gauge groups. We did this in this work and basically confirmed the spectrum, this pattern. So far I've been discussing only F-theory and M-theory. Now let us go back one step and ask, how does this compare to the type 2b limit? So you might ask, now that we finally have F-theory, why bother about 2b? Well, irrespective or independently of our personal romance with intersecting brains, it is certainly useful to check if the intuition that we have and that we have about brain models from the type 2 perspective, if this intuition is still correct or if it is misleading in F-theory. And I learned yesterday in Marianne's talk how to give the answer by posing the question. So indeed, it is possible to basically use and stick to the intuition from type IIB, as we will see now. Namely, one has to consider now as a nice exercise the Zen limit of this U1 restricted Tate model. The Zen limit is defined as type IIB compactification on a Calabi-Yau threefold, which is the double cover of the F-theory base. There is a problem here, namely in the presence of an E6 point, which is something inherently F-theoretic. There is a global obstruction to taking this limit smoothly. This just means that there are certain models which do not have the E6 point. These are non-generic models, and these correspond to the uplift of type IIB models. The generic F-theory model with this E6 point does not correspond to a smooth type IIB model, just as expected. So whenever we want to compare now with type IIB, we have to make sure that this E6 point is absent. So again, this is just for the sake of this comparison. This translates into simple topological constraint that one has to fulfill. And the downlift of this to type IIB is then nothing other than just a model with U5 times U1 gauge group, so the gut brain and an extra U1. And note that, as always in type IIB, we get one extra U1 from here. So this is then the setup, gut brain and its orientifold image, extra brain and its orientifold image, U5 times U1. So first of all, let us see how do the U1 factors compare in both pictures, because the U1 in our case now came about very surprisingly, at least to me. It wasn't really localized on any of the other brains, or nothing split, no brain split in this sector, so it might be a bit mysterious how the U1s actually come about. And the key point to realize is that out of these two U1s that we have in type IIB, one of them is generically massive, is massive even in absence of gauge flux. This U1 decouples in F-theory. On the other hand, the orthogonal linear combination remains massless. I mean here, massless prior to switching on gauge flux, so it's geometrically massless, if you like. And indeed, it turns out that this U1 is precisely the U1x that we had in F-theory. One can confirm this by computing comparing the charges, for example. One can then go on and compare the fluxes. Indeed, this U1x flux is just the flux that corresponds to this massless combination of U1s, namely a flux F on the first brain and the flux minus F on the second brain, so that it really corresponds to this linear combination. So the U1x flux that we have there is just the U1x flux also in type IIB. One might now think that in type IIB one has so many more fluxes. Where are they, all of these fluxes in F-theory? In fact, this is already not true, because we have to take into account in type IIB the D5 tadpole, which is very restricting, surprisingly restricting, and it turns out that apart from this flux, for every F, we have only one more possible flux, and this possible flux is proportional to the 7 brain class on this on this U5 brain. So we only have, we only have one more extra flux. This depends on a discrete parameter here that we can turn on. It is a flux in the massive U1A. So what does this flux correspond to? It turns out this flux just corresponds to the extra flux that we still have in F-theory, namely the so-called spectral cover flux, which I thought that Sakura would introduce in detail. So it's my job now to do this. In addition to these U1 fluxes, one has one more linear combination that satisfies all our constraints for free. This linear combination is fixed completely up to a prefactor, which has to be chosen such that everything is well quantized. And surprisingly enough, it turns out that this flux is precisely this extra flux in U1. This is surprising because this flux has an interpretation in terms of a spectral cover. There it is, just the flux associated with the orthogonal SU5 that we get by breaking E8 down to SU5. This has nothing to do with any U1 whatsoever. For a long time, many people, including myself, thought that this flux is generically F-theoretic. We don't have it in type IIB because we don't have this underlying E8 structure. This is all not correct. The flux is just the flux that we have in type IIB. So things are just the way the way we are used to them, except that they might come in slightly different clothes. Okay, in the remaining few minutes, let me briefly sketch the last aspect, namely D3 M5-instantons in the context of F-theory model building. As we heard in several talks today, and it was in particular reviewed by Miriam, there's been a lot of work on this recently, beginning with Blumhagen, Collino, et al. In the context of, without it, in the context of F-theory model building. In our work, we analyze two aspects of these M5-instantons, the M5 partition function and their comparison with, or the structure of the M5 partition function and comparison with the 3-instanton limit, and the bearings of gauge flux on M5-instantons, which is important. On the first part, I really don't want to spend too much time now because this was discussed in detail in the talk of Max Kerstan. Basically, we're in the framework of an M5-instanton that wraps a vertical device, so the base and the elliptic fiber over this. These are hard to describe because they host self-dual two forms with chiral two forms with self-dual three-form field strengths. One can, however, define an auxiliary action and determine and compute the corresponding partition function. This partition function has a classical piece, a sum over the three-form fluxes, and a quantum piece. This quantum piece carries a lot of moduli dependence, which is very hard to get in this context, but what is simple to, or relatively simple to get, is to perform this classical sum. This, in fact, was outlined in these papers and in much more detail in this paper, and we applied this now in the F-theory context, computed this classical piece, and found perfect match with the sum over instanton fluxes that had been introduced previously in this paper for O1 E3 instantons. Second, what happens now to M5 instantons in the context of G4 flux? This auxiliary action, apologies that this was so fast, this auxiliary action here now picks up a piece that depends on the pullback of G4 to the M5, and it is therefore clear that in the presence of non-trivial gauge flux, the instanton contribution and also the partition function must be modified. In fact, if we're interested only in the KKLT type superpotential that has no charge matter contributions at all, the pullback of this flux to the instanton must vanish. There was a sweet argument by Donaghy and Weinhold that simply pointed out that already now this path integral piece is basically a delta function. More microscopically, the pullback gives rise to a Fried-Witten anomaly, as was pointed out and also used in similar contexts in these works. So in order to see what the selection rules are for an M5 instanton, we should really compute G4 on the pullback of G4. This is easier said than done because we need now to know basically all 4 cycles in our instanton and check if G4 has an intersection with those. And in this work, we found that there are basically 2 types of such surfaces. The first type of surfaces is the one that we expect already from the supergravity. Namely, these are those surfaces that we get whenever we have a massless U1. Just 30 seconds. Whenever we have a massless U1, we can construct a surface from this resolution divisor which lies inside the instanton. The corresponding overlap just reproduces the supergravity charge and therefore gives rise to the charge of the instanton, just like in type 2. There is an additional type of surfaces, however, which are not accounted for by these massless U1s. Namely, one can construct surfaces that are not contained in H22 vert, in other words, which are not algebraic for generic complex structure, but with the overlap of which with the gauge flux can nonetheless be computed. And we gave an argument that these should actually just account for the massive U1 selection rule in the context of a type 2b orientifold. So one last thing I want to clarify, this analysis was entirely in the language of F and M theory. In case we have a U1, a type 2b limit, then this selection rule reproduces this massive U1 selection rule. But even if we don't have this limit, the selection rule remains, we believe. And therefore, again, I would conclude that the intuition about zero modes that we have from type 2b holds also in M theory. So quick conclusions. Explicit resolution of singularities is important for model building for gauge fluxes. The relation to type 2b is more straightforward than we might have thought. And the structure of the partition function of M5 instantons, at least the classical piece, nicely agrees with what we have for flux instantons in type 2b, and also the selection rules can be computed. But for this, we need the fluxes. This is why it has taken so long until one could analyze this. Many open questions, in particular in the context of these M5-instantons. Miriam and Jim also discussed this in detail. It would be wonderful to have a better microscopic picture for M5-instanton, not just these selection rules, these indirect selection rules which I gave. And finally, one very puzzling thing to me, what happens to M5-instantons with H flux that induces chirality? Maybe this is actually related to the instanton effect that Kummerin proposed in his talk. I don't know. We'll see. Thank you very much for your time.
Questions? Vivian?
Yeah. You hope to develop techniques to get information on vector pairs, not just on the Carol index.
So these vector pairs will be present in this quantum part of the partition function. Basically, the vector pairs they could be thought of. So in this picture, this is a bosonic picture, if you like. Here we really integrate over the bosonic fluctuations, but this integral here is indeed in structure exactly the same integral that we would encounter also in type IIB. There were a nice series of papers by Baumann et al. Which showed that the one loop correction to the gauge kinetic function precisely reproduces this information on vector like zero mode. So whenever a brain touches or hits, we get a zero. The same thing happens here, and we believe that in this approach, it should come out of this factor. We haven't made this explicit because we're not working in a model with heterogeneous duality or what. But I suppose that is hidden in there. But I agree that it's very hard to make explicit now, in particular in a geometry. Probably hopeless by this approach.
Questions? Okay, let's thank Timo Weigand.